Okay, welcome everybody. I think we're good. Yeah, no latent audio getting through or anything. So, I think we're good. So, welcome back. We are continuing with our discussion, moving our way through the course, looking over things today. I think we're at a good spot. We're kind of on track like we should be. We're not going to have to rush through the end. Where we're just trying to cram things in at the end, that can be a little difficult. We're just going to move ahead. We are getting into topics that are a little bit more complicated. It's not just necessarily memorize and move forward. And I always kind of say you shouldn't be memorizing too much math anyways, but a certain amount of it is sort of to be expected. We're entering into areas where it's just a little bit more like the memorization is going to help you less and less, and you're going to benefit more from the experience of doing different problems today. And I want you to remember that the problems we're doing today, there are easier ways to do it, but that's because they're very simple versions of the problems, right? So some of the stuff we look at today, you can go, well, I can just get the answer by looking at the graph, right? But that's because I'm trying to keep it simple while I give you these introductory, an introduction to the methods. But once those numbers don't happen on nice grid lines, once your solutions have square roots of 7s or 3s or something in them, or fractions, you can't just look on the graph and get the answer. You're going to have to use the algebra part. So make sure that you're getting both, right? Everything in this class is really the algebra and the graph walking hand in hand together, working together. Not necessarily like, well, how can I use one to avoid the other? You want to do one and then use the other one to check your work and to make sure that you're thinking about it correctly before you get 5-6 steps in and realize that you're doing it wrong. So we're going to look at that. I do have an unfortunate announcement. I do not have your exams yet. So there was a miscommunication, I'll say, with the testing center. So they used to give us a preference. Do you want us to put the tests in your mailbox, or do you want us to send them to you electronically? So I had instructed them, send them to my mailbox. That way when I got back to town, I can just pick them up and grade them right away. They don't do that anymore. That is no longer an option. So then I just said, okay, well then send them to me electronically. And I guess they didn't get that by the end of the day or something. So that didn't happen. So Monday, one way or another, I will get those tests. So when they're open again on Monday, if I have to go to the testing center to get the tests, I will do that. And I will get them all graded so that on Tuesday, you can have the benefit of knowing what your grade is. And then I will definitely make sure that you have, one way or another, you have the option of taking the retake, right? At least it will be available to you. Even if that has to happen in week 6, I will make sure that that's available to you, but I'll try to make sure that it's available for part of week 5 as well. Okay, so that's an option. I'm sorry I don't have your test back. Sometimes they make changes to different systems at the school, but we're not always notified about them, and so then, I don't know. It was definitely not made clear to me that they don't give us the hard copies anymore, that they just scan them and send them to us. So that kind of threw things off. So I apologize for that inconvenience. I know it's frustrating when you take a test and you're like waiting to get the results back. I know I was always frustrated with that. That's why actually I'm generally quite good about getting tests back. Almost always I get tests back the next time that I meet a class. I work hard to do that, but there just was a mix-up between some kind of a mix-up between me and the testing center. So next time, in future semesters, I'll sort of know their updated system. I apologize for any inconvenience this has caused any of you who have studied. I get it. You want to know your grade, and that's reasonable. I promise I will get them to you as fast as I can here. Okay, so thanks for being understanding about that and being patient about that. It's not just that I'm letting it go. I'm working to get those, but they're only open Monday and Tuesday, so I can't really interact with them outside of that zone. Okay, so we're moving ahead with things, and we're getting into chapter 5 today. One question that did come up on the homework, and I answered this student directly but I just wanted to mention it for other students who may be missing problems for the same reason. So with logarithms, when you're solving some of those equations, there is more than one way to solve some of those equations. Sometimes you could use the natural log, you could use the common log, or you could use the log of whatever base is happening in that problem. I mean, technically there's a fourth way. You could use any base you want, but there'd be no really reason to do that. So like this student was doing a problem that was a log base 2 problem, and my math lab wanted you to use natural log, but this student used log base 2, which is actually a really good choice. In the real world, solving using log base 2 would be totally acceptable. Like, no one's going to frown on that or tell you you're doing it wrong. Well, some people might tell you you're doing it wrong, but in general, that's a, some math professors and math teachers get real picky about like certain ways. Like, I want this to look exactly this way when you write it. I'm more concerned about, does this person understand what they're doing, and can they get the correct answer using legitimate methods? And if you can, then I'm open to like, well, yeah, I used natural log to do it and I got the right answer. Well, I used log base 2 to do it and I got the right answer. Well, as long as you're doing it legitimately, then that's fine. But the homework is not always that flexible. If you could imagine from a programming standpoint, it's kind of difficult to figure out every different possible log that someone might do and every different way they set up the problem. So it's a little bit limited there. So generally that logarithm homework, they want you using like the natural log is kind of the default, right, for those problems. But to do a log base 2 problem for a base 2 exponential problem is a fine choice to do, okay? Oh, excuse me. Sorry, my allergies have been bad lately. Okay, so we're kind of wrapping up. That wraps up chapter 4. We're going to get through chapter 5, and probably, I'm thinking we're going to get into the beginnings of chapter 6 today. We'll kind of see where that goes. And then that leaves us basically 2 weeks to get through chapter 7, 8, and then your exam. The last day of class is just going to be your exam that you will turn in and be done with. So that's kind of where we're going from here. I will be adding today a couple more like discussions in here. So early on it was about forming study groups and getting to know each other. I'm going to put a few more discussion boards up in here. Easy way to get points. Just come in, do a genuine interaction with the discussion board, and you'll be fine. So just kind of look out for those. There's going to be one for chapter 5 and one for chapter 6, and then we'll probably for 7 and 8 as well, but we'll see where things go from there. So I mentioned I wasn't specifically going to cover systems of equations. You hopefully have learned systems of equations. Also, I have some, the likelihood is you learned systems of equations in grade school, you learned it again in junior high school, you learned it again in high school, and then some of you have learned it again in college. So hopefully you're able to get through those. I've got videos here that were created by me. I think they're pretty straightforward. And in general, if you're confused, YouTube's full of videos on systems of equations. You can watch Chemistry Tutor doing it. You can watch Professor Leonard doing it, who's another very popular YouTube creator that does math videos. All sorts of people out there. So I would recommend looking at that, because I want to look at the things that are a little bit more complicated, which are the other sections, because I think most people can probably handle this from watching the videos. So that would take us to, I'll do a real quick intro just so we remember the basic concepts, because a lot of the basic concepts for systems of equations are going to carry over into nonlinear systems of equations. So I'll go over it quickly, but you'll get to see some of this. Hopefully you're going to go, oh, that's kind of familiar. I remember what's going on there, because a lot of it's that same material. So let's go to nonlinear systems of equations. So I've got a video here. I'll be posting another video later today. I got it recorded, but I haven't edited it yet, and I haven't uploaded it yet. That'll get up there later today. But it's basically the same problems we're going to go over in class. So if you don't watch the video if you don't feel like you need to watch the video, but if you feel like you need to watch the video, you can. And this is just a different example than the one that I did in class. This chemistry tutor video is a little bit different than the one that I did. So let's go over to here, and in fact, that's the problem we're going to do in a minute, but first I want to kind of give you a brief intro as to how things work. So we have equations, right? So we started with linear equations way back wherever, grade school or wherever you did this. You know, you get something like y equals 2/3 x minus 1, right? And you get this line, and you go, okay, so basically here's the graphical representation of a line is a visual representation of the solutions. So any point on this line, I can take those values and that will give me a solution to this equation over here where the first value is an x, the second value is a y. So if I plug that in over here, I get -1 is equal to 2/3 times 0 minus 1. Basically -1 equals -1. That's true, right? So we could do that with any other point on here we want of these infinite number of points. If we take those values and plug them in over here, that equation is going to come out correct, right? It's going to come out true. So that is what a linear equation is. Then we started talking about, well, what if I have more than one equation in my system? What if I have two equations that I want to satisfy at the same time? And that's kind of the part that, you know, we're sort of going through a little quickly because hopefully you've seen it. Well, we've got a red line and a blue line here, right? And if all of the, why am I getting all blurry here? I just downloaded an update for my camera software and now it's acting all kind of funny. Let's see. There we go. Okay, so if all the points on the red line are solutions to the red equation, and all the blue points, all those points on the blue line are solutions to the blue equation, then what is the intersection of these two lines? Well, that would be a point on the red line, and it also would be a point on the blue line. In other words, the intersection of these two lines is the solution to the system of equations. A system of equations just means we're looking at both of them at the same time, right? We don't just want to satisfy one equation, we want to satisfy both. Well, it stands to reason that the intersection point is a point on both those lines. It will satisfy both of those lines. So if we take 2.25 for x and 0.5 for y and we plug them in, they'll work in both of these equations. Okay, so that's all we're doing from a conceptual standpoint with systems of equations, is you're just satisfying both at the same time. Some of you may have heard this before called simultaneous equations. It just means the same thing but with a different name. Okay, so we can see right here that we get an intersection point. Now, like in this case, this one still comes out fairly well behaved, but you can see we are getting fractional and or decimal values as our solutions, which generally can come up a lot, right? You can end up with your intersection point being a square root or a fraction, a more complicated fraction that's a little harder to see than like 0.5. So your solutions can get more difficult. This is why it's really important that we have algebraic methods for solving systems of equations, because the algebraic methods will be exact, whereas trying to eyeball a graph, not so good. Or even if you do one like this, let's do it this way. I think this will mess it up. See here, when you look at those and you go, oh, 0.167, that's a numerical value, right? Yeah, that's an approximation. That's not the exact value. And when we're doing mathematics, you want the exact value generally because you want to be able to do the most accurate work you can do. If you're trying to maximize profit for your business, you don't want to like, oh, it's like, I want to kind of maximize profit. You want to maximize profit, right? You don't want there to be any waste because that's money that isn't going in your pocket, right? So that's our system of equations. We have two methods for doing this algebraically. The substitution method, where you solve for one variable, you substitute into the other equation, you kind of go from there. And then we've got the elimination method, which is also known as the addition method. So You know, some books call it addition method, some books call it elimination method. You've probably seen it a few times previously in your math classes. We're going to use basically those same methods again, but we have to pay attention to the fact that today we are going to be dealing with nonlinear systems, and so that actually opens up things a little bit more where we have to be careful about our conclusions. The systems of linear equations are simplified by the fact that they're linear. So for instance, right here, I'm looking at this intersection point, and I know 100% that is the only solution. That is the only intersection point in this whole graph, because, well, what if there was another intersection point? Well, that would mean that one of these lines had to curve back up, or both of them, and kind of meet up somewhere else. Well, these are straight lines. How are they going to curve and meet up somewhere else? They can't. But when we're dealing with systems of nonlinear equations, they can curve and come back and meet someplace else. So whereas with our systems of equations that involved linear equations, you only had a couple outcomes. You were going to have one solution, which is what happens most of the time when you solve those. You were going to have zero solutions, which is to say no solution. Or you were going to have an infinite number of solutions, which basically means they were the same line. Right? The two lines are just, they look different, when like you don't recognize they're the same. They look different, but they're right on top of each other. Then they share an infinite number of points, right? And we'll return to those concepts later. Probably will come up today. I think it comes up next time, if I remember correctly. So we want to look at that situation so that we know what we're looking for when we solve systems of nonlinear equations. Okay, so let's look here. Here's a situation where I have a parabola and a circle, and this is the first example we're actually going to work through. But you can see I've got my a slider over here, so whatever I change the a value to over here, it just becomes this value in this equation. So right now, it's graphing y equals x squared plus 4 because a is equal to 4. If I change this to a 2, now it's graphing y equals x squared plus 2. Right? So I'm just using that to move that around. But I want to show you something. I want to show you, you know, with our lines we said, well, there's only three possibilities. You have 0, 1, or infinite number of solutions. Well, look what we have here. We have a parabola and a circle. And if we look at the orientation that our parabola and circle are in right now, there's no solutions because there's no points of intersection. There is no point that lies both on the parabola and the circle at the same time. So right there by looking at the graph, no solution. I know it's no solution. Okay, well, let's just change this, just this value in this parabola, this parameter. Let's make that a 3 now. Ooh, so now my parabola is coming down and just tangentially touching the circle, and then it goes back up. So that looks like one point of intersection. So now that I've just changed that parabola a little bit, it looks like now we have one solution. So a moment ago we had 0 solutions. Now we have one solution. Okay, let's move it a little bit more. Ooh, now we have 2 solutions. Now there's 2 solutions to this system. Okay, let's go a little bit more. Oh, 3 solutions, right? There are 3 points of intersection, so there are 3 solutions to this equation. What if I go a little bit further? Now there's 4. Now there are 4 points of intersection, and if I keep going, okay, now we're back to 2. Now we're back to 0. So you see how you can't really predict nearly as well how many solutions your system is going to have. With systems of linear equations, we pretty much knew most of the time we were going to get one solution. Every once in a while we'd get no solution or infinite number of solutions. But when you're dealing with nonlinear systems, a lot of times you just don't know, which is why it's really helpful to put these in a graph. So if I'm going to solve a problem like this, first step for me is usually put it in a graph. Okay, so I can get a sense of what it looks like. This is a game you're going to play in algebra all the time. Like you're just, in calculus. Those of you who are going on to calculus, you're just going to have your graphing calculator with you, or if you tend to be in front of a computer, you might have Desmos open. But you just do this constantly in calculus. Like you're working on something, and then you go, I wonder, and then you look at the graph to figure it out. Okay. So what about this? Look at the graph to figure it out. You're just always checking that graph. So it's a good practice to get into, right? Especially in the day and age where more and more professors are recognizing that, like, yes, it's legitimate to look at a graph. It's not cheating as long as you don't cheat yourself out of the learning. It's a learning tool, right? So let's go back and we're going to solve this one right here. So this is effectively y equals x squared plus 3, because my a value is set equal to 3. And then we've got this circle down here. Now, we can tell by looking at this graph, we think we know what this intersection point is. It sure looks like it's going to be 0, 3, huh? Yeah, it is. But again, if we're dealing with problems that are just slightly different, where like if I move this down here, now all of a sudden it's not at all clear what those point of intersections are. So I'm doing some simple problems just to make sure everyone can follow along so the numbers are not too complicated. But don't skip that and go, well, I don't even need to do the algebra part, I'll just look at the graph. Because like an intersection point right here, you can see those are approximations. Those aren't really good enough for figuring out the exact values that we're dealing with right here. So that's why we care about the algebra, because we want to always have a method that will work for us exact. Okay, so let's put this back to 3. That's the problem that we're looking at. So we're looking at y equals x squared plus 3 and x squared plus y squared equals 9. So let's go back over here. So this is our system that we're looking at. Y equals x squared plus 3 and x squared plus y squared equals 9. Now, we are going to play a very similar game to the one that we play when you solve any system of equations, which is you kind of put on your detective hat and you look at your system and you try to figure out, should I solve this using substitution or should I solve this using elimination? And you kind of look for clues. And it's a little bit more straightforward for the systems of linear equations. We have some pretty good guidelines about, well, when you see this, use substitution. When you see this, use elimination. And it's not a lot more complicated in this case, but it is a little more complicated. So, and it, just like the other system, it's up to you, right? If one student decides to solve one system using substitution and another student solves that same problem but with elimination, it doesn't mean one of them's wrong. It just means that probably one of them did a little bit more work than they needed to do. But who cares, right? You know, when you're an engineer or mathematician or scientist or whatever, sure, you want to be as efficient as possible, but the goal is getting your work correct, right? And if that took you a couple extra steps, big deal, right? Okay, so what am I going to do here? I've got a situation that, so I'll give you a little bit of a hint. Usually, like this is the problem we're going to do in a few minutes. See how in this problem down here, every variable is being squared? In a problem like that, you're probably going to use elimination / addition method in order to solve that. But if you don't have that, like in the problem we're looking at now, you might try substitution. Okay, it's not hard and fast that you have to do it that way, but you might. And you even have to be a little bit careful, because if you substitute poorly, if you make a poor choice for substitution, you're going to create an equation that's really hard to solve. And obviously we don't want that, right? We want to create equations that are easier to solve. We want things to get easier, not worse. So it would be very reasonable, for instance, for you to look at this and say, well, look, y is already solved for. Why don't I make that substitution? Well, when you do, look what happens. You're substituting into y squared, which means you're going to be squaring whatever you put into that second equation. But one of the things you're putting in is a square, which means you're going to end up with an x to the 4th. So now you have a 4th degree polynomial to solve. Probably skip that route, right? I mean, it's not the easiest way to do it. You can do it. It's definitely not the easiest way to do it, okay? So that's okay if you do it that way. What I'm going to notice here in this problem is I'm going to say, well, I have an x squared term here and an x squared term over here. Why don't I use those for my substitution? Yeah, why don't we? We were always saying when you were solving systems of equations, we were always saying, like for substitution, solve for one variable, solve for one variable. But you don't actually have to solve for one variable. You want to solve for something that occurs in the other equation, right? That's another way of doing it. It's just that when we were solving linear systems, everything was just a variable by itself, like y. There were no y squareds or x squareds, right? So what I'm noticing is that I have an x squared term here in my first equation and an x squared term in my second equation. So why don't I go ahead and write one of those equations in terms of the x squared term. So it's basically the substitution you're used to. It's just that we're not just substituting a variable, I'm substituting a version of that variable that occurs in both ways. I mean, you could solve for one variable if you want, but again, it's going to make it a little more complicated than we need it to be. So I took the second equation and I just subtracted y squared to get x squared equal to 9 minus y squared. So notice how I can do a substitution now. I know what x squared is equal to in terms of y, so I'll just substitute up here this x squared for 9 minus y squared. That's what we're going to do there. So when I do that, I end up with the substituted version of the first equation. So y equals x squared plus 3 becomes y equals 9 minus y squared, because that's our x squared term there. So the thing in parentheses is the x squared term, and then plus 3. All right. Please feel free to ask questions along the way. If I'm losing anybody, ask a question and I can go back and explain, because I know sometimes it's hard to keep track of all this stuff. So make sure you ask, okay? And here's the whole goal, is that we now have one equation and one variable. We started off with two equations and two variables. Those are tricky to solve, but we know how to solve one equation and one variable. In fact, this looks like it's going to end up being a quadratic. Great, we know how to solve quadratics, right? Hopefully it'll be factorable. Worst case scenario, we can use the quadratic formula and get that thing solved for. So I'm going to take a couple of steps to just go through and solve this equation. Right, so I'm going to work to get everything on the left, get things simplified, and get them on the left side of the equation, and we end up with y squared plus y minus 12 equals 0. Oh good, I think that might be factorable. So we're going to go through and factor it. You get y plus 4, y minus 3 equals 0. Right, we've got it in that factored form, and then we just carry it out and solve it, and we get that y equals negative 4 or y is equal to positive 3. Those are the two outcomes. Now, here's where things are a little different now, because before, when we were solving systems of equations, you end up with one answer, right? You would solve your system of equations, and then you'd get maybe x equals 7, or you solved it and you'd get y equals 5, right? You just get one number. Here we have two. What do you mean there's two? Y equals negative 4 or y equals 3? Well, which one is it? Well, the answer is we have to test them both, because sometimes they both will lead you to solutions, sometimes neither one will lead you to solutions, or like in this case, one of them is going to work and one of them doesn't. But how do I know which one works and which one doesn't? Well, I have to test them in order to find out. So that's what I'm going to do. So we're going to go, okay, so now we're going to restrict ourselves. We're going to say, well, if y can equal negative 4, but also y can equal 3, I'm just going to restrict myself now to the time when y is equal to negative 4. I'm just going to worry about that one for the moment. We'll put the y equals 3 to the side, and we'll get to that in just a minute. But for now, let's focus on y equals negative 4. Well, what do you do in a system of equations when you solve for one variable? Well, you plug it in and solve for the other variable. That's exactly what we're going to do here. So if y is equal to negative 4, I'm going to go ahead and plug that back into one of my original equations to see what that tells us about x. Okay, we want to know about x. So if y is equal to negative 4, I go back to that original equation up here, right? This is equation number 1. And I'm plugging in y equals negative 4 into equation number 1. Okay, now I have an equation I can solve here. And, oh, it looks like we might have an issue going on, because when I subtract 3 from both sides, I get x squared equals negative 7. Now, we learned about complex numbers. Complex numbers play an important role in mathematics. We wouldn't have electronics or processors or any computers of any kind, or even, most large-scale electrical work would not be possible without complex numbers. But in many instances, complex numbers are not going to be helpful to us, right? It really depends on what you're doing. In this case, we are dealing with real valued solutions. So the fact that x squared is equal to -7, that kind of tells us that this is going to lead to a no real solution scenario because we're not going to get any real solutions here. So that is kind of a dead end where y was equal to -4. That's not going to lead us to a solution. So we go, okay, we see what happens when y equals -4. It doesn't lead us to anything. All right, well, let's check out that other scenario, right? We said y was either equal to -4 or y was equal to +3. Well, y equals -4 didn't work out for us, so let's try y equals 3. I'm going to say, okay, well then let's get to that scenario where y is equal to 3. We're going to try that one out. Okay, so just like we did before, I'm going to go back to one of my original equations, whichever one looks like it's the simplest one to deal with, and I'm going to plug in y equals 3. And that's then going to inform us about the x's that go along with that value of 3. Okay, so if I plug that in, I get 3 equals x squared plus 3. Of course, if you subtract 3 from both sides, you're going to get x squared equals 0. And of course, if you solve x squared equals 0, you're going to get x equals 0. And what does that tell us now? That tells us, well, we said when y is equal to 3, that x is equal to 0. So what that's really done is it's given us the solution that we were looking for here, which is that x equals 0 and y equals 3. Or, like we sometimes do, we draw them on a graph and we get that our solution is 0, 3. So remember, we can interpret these as the point 0, 3. And sure enough, if we go back to our graph, that is in fact where our solution is sitting, right at 0, 3. Okay, so we were able to find that intersection point. So that's all there is to this. It's not really like a whole new thing. You just have to, the main thing you have to look out for is these extra solutions that you can end up with, where you could end up with, like the next problem we're about to do has 4 solutions. So you just have to remember how to move through the mathematics in order to get your 4 solutions that you're looking for. Okay, is there any questions on that one? Are we good? We're doing good. Okay, great. Then let us move ahead. See, this is, I don't need that one anymore. Oops. Let's get all those out of there. So our next one is 2 ellipses. 3x squared plus 2y squared equals 35. 4x squared plus 3y squared equals 48. And we've got them here graphed. Kind of looks like they match up over here, but they don't. If we zoom in, we can see there's a little bit of distance between those lines. It's just hard to see when you're zoomed out all the way. So it kind of looks then like there's 4 solutions, kind of one in each corner. I mean, it's an ellipse, so calling it a corner is kind of weird, but you know what I mean. So like those, we can see the 4 areas where it looks like we have a solution. So we need to figure out what those are. Now in this case, it's a little harder to see. You might be able to kind of pinpoint it, but we want to do it algebraically so we know for sure what those points are and we know how to get them. Okay. So let's go back over to here. And here we have our problem. 3x squared plus 2y squared equals 35, and 4x squared plus 3y squared equals 48. We want to solve this system of equations. Now, usually at this point, when you see a problem like this where all the variables are squared, then you're probably, the easiest way is usually going to be the elimination method. So we just solved one with the substitution method. Now we're going to look at solving one with the elimination method because I think that's going to be a little bit easier here. So we're going to, play similar games to what we did before. For elimination method, our goal is to get some variables to cancel out. Right? We want the variables to cancel out. So I either want my x squareds to cancel or I want my y squareds to cancel. It doesn't really matter which one you pick. I'm going with getting my y squareds to cancel just because 2 and 3 are smaller than 3 and 4. And I just think it's going to be a little bit easier to deal with. But it doesn't matter. If you wanted to cancel the x squareds out, that would totally work for you. Okay? It would, the perfectly legitimate way of doing the problem. So what I'm going to do then is multiply the top equation by -3 and the bottom equation by positive 2. And what this is going to do is give me a negative 6y squared in the first equation and a positive 6y squared in the second equation. So that just like we do when we do elimination method, these terms right here are going to cancel when I add these two equations together. That's the whole point, right? So I multiplied equation 1 and equation 2 by values that we're going to get one of these to go away. Right? One of them was going to disappear. That was the idea. So equation 1 got multiplied by negative 3. Equation 2 got multiplied by positive 2. We can see those 6y squareds are now going to cancel each other out because they have opposite sign. Remember to get that opposite sign. Sometimes people will get like positive 6y squared and positive 6y squared, and then they cancel them, but that would actually be 12y squared, right? So make sure you have an opposite sign in there so they're actually canceling each other out. And then you can see this simplifies significantly when we go through and solve that. We're going to get negative x squared equals negative 9, because negative 105 plus 96 is negative 9. Negative 9x squared plus 8x squared is negative 1. So we're going to go ahead and multiply both sides of that equation by negative 1. And then being careful here, because this is where I see a lot of students go, oh, well, if x squared equals 9, then x equals 3. Be careful, x equals plus or minus 3. So we want to think about either the square root property or whatever it is that, you know, or allows you to remember, like, oh yeah, there's supposed to be two answers there. And yeah, on rare occasion, your two answers can be the same number. But usually in something like this, we'd be expecting two answers. So don't just go with 3. You want to realize 3, but also negative 3 are solutions to this equation right here. Right, so that would be our answer that we've got. X equals plus or minus 3. I mean, that's not the final answer, but that's the values that our x's can take on in this scenario. So now we're going to do it like we did before, where we break it into cases. Well, let's just worry about when x is equal to 3. Okay, so when x is equal to 3, then what happens is, all right, so we're just pretending for the moment. Let's just live in the land of x equals 3, and then we'll deal with x equals negative 3 in a moment. So I go back up and I grab one of these original equations, and I'm going to plug x equals 3 into it. So I'm taking this first one right here, right, equation number 1, and I'm going to plug in x equals 3 to it. So we get this. So 3 times 9 plus 2y squared is equal to 35. Whoops, that was not the right key. There we go. So what that's going to do then, 3 times 9 is 27, plus 2y squared equals 35. So all I'm doing is I'm simplifying that x part of that equation. Then we've got 2y squared equals 8, because I'm subtracting 27 from both sides of the equation. Well, if we divide both sides by 2, that tells me that y squared is equal to 4. And if y squared is equal to 4, then y is equal to plus or minus 2, right? Again, using that square root property, we get that y equals plus or minus 2. So now wait a minute, what's going on here now? So I've got when x equals 3, I've got that y equals plus or minus 2. Well, which is it? Is it plus 2 or is it minus 2? And the answer is it's both, right? So our constraint says that when x is equal to 3, y is equal to 2, and also there's a possibility where y equals negative 2. So it's giving us 2 points here. We're getting 2 points from this one problem that we just solved. So we get 3, 2, right? Because our x is 3, and our y is 2 or negative 2, so 3, 2, 3, negative 2. Those are two of our solutions. And if we go back to our picture and we graph those, sure enough, that looks like two graphs for the points of intersection. So it looks like we're on the right track. Now in this particular case, you happen to get a lot of symmetry. So once you figure out these two, you might be able to figure out these two over here. But again, I'm trying to show you the algebra so that you can do the harder versions of these when you get to those. Right, so then we just go back over here and we go, okay, well, that's when x was equal to 3, but what about when x is equal to negative 3? So now we're going to play that game. We're going to play the x equals negative 3 game, and notice what happens here. This just happens sometimes. This doesn't happen with every single problem, so, you know, just pay attention. Don't, like, assume it's always going to work this way. But what happens in this case is that since all of our terms are being squared and our x values were 3 and negative 3, well, look what happens when I plug negative 3 in here. Remember, this was a 3x squared? Well, then I'm still going to get 9 for the input of my x, right? I mean, we put in negative 3, but then we squared it and it became a 9. And look, we're going to get 27 here. So all that math is actually going to turn out the same way, right? Right down till we get to the bottom. And this time we're going to end up with negative 3 comma 2 and negative 3 comma negative 2. So we just get these other two solutions that are over here on the left that end up being correct. And if you zoom in, you can see, yeah, those look correct. And of course, you can always check your work. This is one great thing about systems of equations. Finding a solution is usually a lot of work and it's difficult to do, but verifying your solution is very easy. All you have to do is plug your values into these original equations and just verify that they work. And it's worth it. Considering the amount of time that you put into a problem, you don't want to get it wrong, right? You want to catch any mistakes or little errors. You want to verify they're correct. So you could really be careful by, like if it was a test or some important work, plug it in and just verify that it works. But we can also see here from the picture, the graph is verifying that what we found is correct, what we found algebraically. Okay? So it's the same kind of game that we play with systems of equations. We're just doing it now with nonlinear systems of equations. And you can't memorize every possible combination. You can't memorize, well, here's with a line and a circle, and here's with an ellipse and a circle, and here's an ellipse and a line, and here's an ellipse and a hyperbola. And I showed you how in each, in some of those cases, by transforming, performing transformations on those graphs so they move around, you end up with a different number of solutions. So you just always have to be like looking at the graph, looking at the algebra, and making sure everything makes sense. So it's kind of like having two different languages, right? You have to be able to work well with the algebra and understand how that works, but then you also have to be able to work well in the graphical environment. And in fact, when you can understand both of them, then they improve the other one, because they can tell you information that helps you do the other one and also help you catch mistakes before they become too big of a problem. Okay, so that's two examples of how you solve the non-linear systems of equations, right? That's how that's going to go. Is there any questions on that before we move on to the next section? Now everybody's good? Okay, then let's move ahead. See if I can find the right tab here. Here we go. Here's the one. So systems of equations, systems of inequalities is what we're looking at now. So this is all about how do we represent systems of inequalities. Now here we end up with very large solution sets. In fact, almost always they're an infinite solution set because you have an infinite number of solutions in your set. And this is why we usually represent these in a graph, because it's pretty hard to describe these regions algebraically in a way that is like clear and easy to understand. If you put it on a graph, people just look at it and go, oh, okay, I see where the points are. But it's a little harder to describe from an algebraic standpoint. So what we want to do is start understanding, well, what do we do with inequalities? See how I have an inequality here? Y is greater than or equal to 2x minus 1. So I'll kind of review how this works. This is what it looks like. You end up with a line and then a shaded region. So all these shaded points here are solutions to this top inequality, right? If you take any of these points, how about 0, 5? If we plug 0, 5 in here, I get 5 is greater than or equal to 2 times 0 minus 1. Yeah, that's true. Pick any other point over here you want, and it's going to work out in this inequality. But I got this by having Desmos graph it for me. How would I know what that region is without just having Desmos do it? And this is something that you will use for lots of tools, depending on what you do. If you're doing optimization, you're going to do stuff like this all the time. Like I've been messing around a bit lately with machine learning and AI stuff. This kind of stuff comes up all the time in it. it comes up in many, many areas where you're trying to like optimize things and do different things. So so it's important to like, you may have heard these before, we call them feasible regions, where you portion off a part of the graph and say your optimal solution must exist in this part of the graph, and then you try to find it. You use it for that all the time. So how do we actually get this shaded region though? So what you do, the first step is you just momentarily pretend like your inequality is an equation. We're not permanently turning it to an equation. Sometimes students get confused and they go, oh, well, you said to just turn them all into equations. Well, if we did that, we wouldn't have inequalities in the first place, right? The inequality means something. There's a reason that we have it and we learn about it. But momentarily, just for an instant, we are going to pretend it's an equation because that's going to help us. So notice right here when we've got this region, right? What do we have? We have a line and a shaded region. Well, notice that the line, when we momentarily pretend that it's an equation, notice that that is the boundary line. That is the part that separates the shaded region from the non-shaded region. So that's what we do first, is we say, well, if I want to graph y greater than or equal to 2x minus 1, first I should graph the boundary, which is y equals 2x minus 1. So right there. And I go, okay, I've got a line. How did I know to make a solid line? If your inequality has an or equal to part, so in other words, greater than or equal to or less than or equal to, then you make it a solid line, because that means that the points on your line are actually solutions, not just the boundary, they're also solutions. Okay, so in that case we draw it with a solid line. You can see down here, notice how when I do this one, we're going to talk about in a second. I don't know why I keep getting blurry here. Download the new software and then it's making me all blurry. There, stop doing that. Okay, so see how here it put these dashed lines? But that's because this inequality is not an or equal to, it's a strict inequality, where it's strictly less than, or if you have a problem that's strictly greater than, then your boundary line should be dashed or dotted, because that indicates that the points that are right on the edge of the boundary are not solutions this time. So up here, points on the line will satisfy this original inequality. Down here, points on this line will not satisfy this inequality right here. Okay, so that's the difference between when you make the dashed line and the solid line. Okay, so let's go back up to here. Okay, so I've got my line here, and I have to either shade one side or the other. Now we know, because I cheated and we peeked, right? We looked at what it was going to be. So we kind of know, but in the problems you're going to do in the future, you don't know what they're going to be. So how do I know if I'm supposed to shade this kind of top left side or this bottom right side? And the answer is you pick a test point. So you can pick any test point that doesn't fall on the line. You can't pick a point on this line, but you can pick anything off to the side. The origin 0, 0 is a great point to pick because it's just really easy to deal with. As long as your line doesn't go through the origin. But you could pick any point. Like, for instance, let's take the origin, 0, 0. So x is 0 and y is 0. Well, if I go to plug it in here, in my original inequality, what do I get? 0 is greater than or equal to 2 times 0 minus 1? Yeah, 0 is greater than negative 1. That's right. So that would indicate to us that we should shade this side over here. Well, what if I'd picked something on this side? What if we pick 5, 0? Well, let's see. When I plug that in, do I get that 0 is greater than or equal to 2 times 5 minus 1? That would be 0 being greater than or equal to 10 minus 1. Is 0 bigger than 9? No. So see how when we graphed on this side, we got the right answer. That tells us that the solutions are on this side, where our test point was. The second time, we picked a test point on this side, and we got a false answer when we plugged it in, meaning these are not the solutions, which would indicate to us, jump to the other side and shade that side in. So that's why it looks like this. Okay, so it's just you graph the line, like just beginning algebra, graph a line type stuff. And then you pick a test point. Any point you want not on the line, you pick the x value and y value, plug them in, and you shade the side that makes it true. So in this case, it looks like this. Okay, so that's how you graph one linear inequality. Hopefully you remember that. That's something that is kind of prerequisite material for this course. What we're about to do is just an extra step, which actually is not any harder. It's actually, if you understood everything I just said, you're going to be able to do the whole problems no problem, right? The place where people get kind of bogged down, I see, is when they can't, like they forget how to graph linear equations, which is kind of wild, but happens more often than you think. But if you can graph the line and then you can figure out which side to shade on, this section's going to be easy for you. Okay. All right, so now let's ignore that one for a second. Let's get rid of this. Let's say, well, what about if I wanted a system of inequalities now? We just talked about how to graph an inequality, but what goes on when I want to graph a system of inequalities? And the answer is I'm going to show you how to do it, because it's like if you understand what we did, and we're just basically going to repeat that process, but it starts to get messy. So I'm going to show you kind of how to clean things up and really answer in the proper way. So let's see. If I wanted to graph 2x plus 3y equals 6, I would graph the line 2x plus, if I wanted to graph the inequality, 2x plus 3y is less than 6, then I want to graph the boundary 2x plus 3y equals 6. So see how I have the line right there? Now, I know we don't have an or equal to up there, but again, this is only a temporary step to help us. This black line is not going to be part of our finished solution. It's just to help me figure out what's going on. So let's even get rid of this one for a minute. And I go, okay, am I supposed to shade this part below the line, or am I supposed to shade this part above the line? Well, again, take a test point. Let's try 0, 0. X is 0, y is 0. Okay, so 2 times 0 plus 3 times 0, is that less than 6? Yeah, 0 plus 0 is less than 6, meaning the origin, our test point, is on the same side as our solutions. If I pick something over here like 5, 5, and I plug it in, I'd get 10 plus 15 is less than 6? No. So then we'd know we're on the wrong side up here. So this indicates to us that our problem should look like this. That's what that should look like. Okay? And notice the dashed line because of the strict inequality right here. Okay, well, how do I put the two together? Now we're doing a system, and we want to think about both of these at the same time. Well, you can see we have 4 regions here. We have the region over here that never got shaded. That means it doesn't satisfy either one of our inequalities. We've got the region up here that was just shaded red. That means it only satisfies the first inequality. We've got the blue region down here that only satisfies the second inequality, but look at the doubly shaded region over here. Those points must satisfy both because they got shaded from both of our inequalities, and that's actually the answer. Now this looks a mess. Like if you turned in an answer like this, you'd get marked wrong because people would be confused. This is our intermediate steps to get to the solution. Okay, now you don't have to do this in Desmos each time because most people kind of get it. They go, okay, I understand this is the region, and then they match it with the homework. However, the homework is asking you, sometimes they'll say like, shade the region. Sometimes they'll say pick the region, or there's a few different variations of the problems. But most people, after dealing with this, can go, oh, okay, I can see how to carry this over to the homework and do it. But you should understand the solution should actually look like this. Right, and you could even add the lines in if you wanted, although not that one because it's not dashed. But you see how right now we're only looking at the region of our solutions? That's the point. That's kind of how we want to do these things. So this is really what the region should look like. Don't think that it should permanently look like this, because that's confusing and too much going on. We remove these, and we just have the one shaded region so it's very clear. Oh, the shaded region is solutions. Everything outside of that is not solutions. Okay, so that's really all there is to doing a problem like that. Now they can get more complicated to where you have some more stuff going on, to where you have systems of nonlinear inequalities, and you can see you're just gonna play the same games that we did in those last 2 sections, right? It's the same stuff. Give me 1 second to see if I missed anything I wanted to say. Yeah, there's an example in the book where they do. Let's go ahead and take a look at that. So what if we have x squared plus, what have I done here? Okay. X squared plus y squared is less than or equal to 9, say. So what if you had to graph like x squared plus y squared less than 9? That's not even linear. Well, you would graph the circle, which is x squared plus y squared equals 9. And then you would just figure out, am I supposed to shade the inside or the outside? Well, guess what? Test point. Test point of 0, 0 looks like it's going to work. So that's why the inside gets shaded, right? Because 0 plus 0 is less than or equal to 9. Okay. What if we change this around to be, instead of less than or equal to, what if this was greater than or equal to? Now look at shading the outside. So it's just a test point, right? Now if you try 0, 0 and x squared plus y squared is greater than 9, 0, 0 isn't going to work because 0 is not greater than or equal to 9. So when it's nonlinear, just do the same thing. Graph it and then choose a test point to figure out where you're supposed to shade the stuff. It's not like, it's not meant to be tricky or anything. Now you can get a few weird situations where you get no overlap, or where you get like, we can actually do more than 2 inequalities. You can have a triangle where you have 3 things that enclose an area, but it's the same idea. You just keep, graph the one part, pay attention to the shading. Graph the next one, pay attention to the shading. Next one, pay attention to the shading. And then you just, at the end, your solution is the thing that got shaded every time. If there was one part that got shaded each time you did one of those inequalities, then that's your solution and you would shade that area in. Okay? You would cover that in. I think people tend to do pretty good on 5.5. So as always, bring questions if you have any. 5.6 is a thing that some of you may do in the future. It's called linear programming. It's kind of, it's about finding feasible regions. It's about optimizing things, lots of things, flow, network, all sorts of things. You can apply it to many, many things to optimize things. That's in 5.6. Most of you will learn that later down the road. Well, some of you will. But if you're going into like a science-y type thing, it's going to come up in a linear algebra class or something like that. You're going to do some of that. So, if you like to kind of nerd out on stuff a little bit, it's definitely a useful section to read through, but we don't have to cover it for this course. But you're welcome to. Okay. All right. Any questions before we move ahead? Feel free to ask if there's a question before we move ahead, but I think people should be able to get through with those. So we're going to start chapter 6 today, which is matrix solutions to linear systems. Okay, so we just learned a whole complicated system for solving systems of equations, but it turns out that, and other types of related things, but it turns out that most of the time when you solve a linear system of equations, you're probably not going to do them by hand, right? So we're going to talk about that a little bit. And it might seem like, well, why are we back to talking about systems of linear equations? It seems like more times than not, you would run across systems of nonlinear equations, right? Because those can have linear equations, but they can have other things in them. And the answer is, those come up a lot, but it's surprising how often systems of linear equations come up as a way to solve problems, like a lot. Systems of linear equations gives rise to an entire area of mathematics, very, very powerful area of mathematics called linear algebra. And some of you will take linear algebra when you get through calculus. So you do your calculus series. For most of you who have to take the calculus series, on the other end, there's going to be 2 classes waiting for you, one called differential equations and one called linear algebra. And linear algebra is an entire semester of learning about, not just solutions to linear systems, but that's like the foundation. You're building on that, and you create, you just find all these tools for being able to solve systems of linear equations and related problems. It comes up all over the place. So, every business out there, every industry or type of business, there are problems, research, all that stuff. Basically, there are problems out there that can be solved with systems of linear equations. So essentially, linear algebra is one of the most important areas of mathematics out there. I didn't really appreciate that when I was younger. I don't know, here's some exercises, they're having me solve systems of linear equations. But it turns out in real life, these things get used all the time. Whatever area of math you're going into, I was in pure math with combinatorics and a little topology. The algorithms that I was writing, computer programs to run algorithms that I was writing, relied heavily on systems of equations, systems of linear equations, solving the resulting matrices, which we're about to talk about, all that stuff, right? So hugely, hugely important. You will rely more and more on computers to solve these things for you, but you have to understand the underlying framework, or how can you tell a computer to solve a problem for you if you don't even understand the problem that you're working on? You cannot. Okay, so when I say, oh, well, you're going to have problems, you're going to have software solve these problems for you, sometimes people go, oh, well, then I don't really need to know the math because a computer's going to do it. You have to figure out what you want the computer to do, how to set up the problem, what your type of solution looks like, all that kind of stuff. And if you don't understand the intermediate step, it's just not going to happen, right? So, but I don't want to knock computers. The computers are fantastic, right? When I was going to school, my undergraduate advisor, he was telling me how when he was in graduate school, which was like in the 70s, back before they had a lot of computers, for his graduate work, he had to solve a system of equations with 100 equations and 100 variables. Basically, it took him an entire semester to solve the thing, because that was back when you had to do things by hand. When I was in graduate school, I was using systems of equations where there were thousands of equations and thousands of variables for the type of problem that I was working on. Luckily, I had access to some powerful computers, and I could just, I created the problem, I created the algorithm, I said, this is what I want you to work on, and let it run for a week, and then it would, it would come back with solutions that I needed in order to do these different problems. So the computers are very, very helpful, and they allow us to solve problems that simply we just could not do by hand, but it is no way a substitute for your brain and you knowing things and having the knowledge, because if you don't do that, you're going to reach a point where you just don't know how to do the problems anymore because you're missing that underlying foundation. So never let computers be a replacement for you understanding stuff. What you really want is a computer to be a replacement for the computation, right? It's kind of a waste for your brain to sit around and do add, subtract, multiply, and divide, because that's what computers can do faster and more accurate than you. But a computer doesn't really understand what it's doing. It's just following directions. It's following commands and orders, right? So you have to know how to set up that problem so that the computer can do the plus, minus, multiply, divide really, really fast for you, right? You want to sometimes people think computers are smart. Computers are getting a little, could be arguable with machine learning that, exactly what's going on with computers, but they still need a human for most jobs at the helm, sort of telling the computer what to do, okay? Okay, so with that said, I'm going to pull up, where was this? We'll go here, go modules, starting on chapter 6. I put the worksheet that I'm gonna talk about, I put it in here so that you could either, if you want to print it, you can, or if you want to follow along and make notes on it, you're welcome to do that. But I'm just going to kind of be going over it. This is a worksheet I used to work on, and I'd have my students go over when they're first learning matrices so they would understand how to do it. So it's just a worksheet to get you to know how to do things. I'm going to go over it in class. You can follow along, make notes, whatever it is that you need to do. So, in fact, let me grab a water really quick. I'll be right back. Okay, so we have these things called matrices, which some of you may have seen before. Matrices is the plural of matrix. So you can have a matrix, or you can have multiple matrices. And what a matrix is a very convenient way of organizing the information that is inherently held inside a system of equations. So what is a system of equations? Well, you kind of play this game with system of equations where the more variables you have, the more freedom you have, because if I have an extra variable and I can set that variable to whatever values I want, that's kind of a freedom, right? And the equations are the constraints. So the more variables you have, the more sort of freedom you have, the more equations you have, the more constraints that you have. But you can imagine we could have systems of equations where, like, I could give everyone in this room, I could say, on a piece of paper, solve this system of equations right now. And if I looked at it, let's just say you all got it correct. We could still line up all of your papers and look at them, and they're probably going to look very differently from each other. Some of you may have picked a different variable to solve for. Some of you may have picked substitution. Some of you may have picked elimination. Some of you have picked a different variable to use elimination, or a different variable to use substitution. There's lots of choices there. So we'd see many versions of the work, and they may all be correct, but that becomes a difficulty when you're trying to, say, program something, right? In the near future, as you progress through your calculus, and especially as you get to your upper division work, those of you who are going that route, you're going to start using Maple, MATLAB, other types of programs to do a lot of your algebra for you. Well, almost always what happens is you're going to be inputting a matrix into the computer, and then the computer goes, oh, I know how to interpret this matrix, and I know what to do with it. Very rarely are you going to be just inserting equations directly. Sometimes, but usually not. Wolfram Alpha can do that. If you put in equations, it'll sort of figure out, oh, do you mean this matrix right over here? But usually it takes you, the human, to sort of set the problem up. Okay, so we have this thing called a matrix. So right now we have, this systems of equations right here. Let's see, I can blow that up a little bigger. So for instance, x plus y equals 1, 2x plus 3y equals 6. But imagine all of the other work that you're going to do on the bottom of your page, right? Your work's going to look different than someone else's. We want to come up with a system where we can cut out all of that stuff that's not important, and we can just come up with like the important information that needs to be carried to the next step. So we create this thing called a matrix. Now the way you interpret this, we have rows and columns. So the way you can think about this, like we have columns in architecture, right? Are columns in architecture horizontal or vertical? Think about like the front of a bank, or some fancy historic building. Columns go up and down, right? They're vertical. So we call the up and down lines columns, and then the horizontal ones we call rows. Think about like a farmer who's planting rows of seeds. Those are horizontal. Okay. Now I mention this because it's really important that you know the difference between rows and columns in matrices, or you're going to get mixed up. If you do the wrong type of operation, it all gets weird. So rows, when I talk about a row, that's a horizontal line. When I talk about a column, that's a vertical line. So just think, architecture and farms, or banks and farms. Banks have vertical columns, farms have horizontal rows. Okay. So what we do is we say that in our matrix, each row, horizontal row, represents an equation, and each vertical column represents a variable or a number. The one at the end can be a number, but generally, you'll get this when you think about them being variables. So I've taken this, our original system of equations, and I've said, okay, we've got two rows, each one corresponding to an equation, and I've got my columns corresponding to variables. So see, I've got my equation 1 and my x column. So what you do is you take the coefficient from your problem and you put it in the matrix. We don't even have to put the variable in the matrix. That's convenient. Now, why don't I have to include the variable inside the matrix? How do I know if it's an x and a y? Well, remember, each column is representing a variable. So I know that the number in my first column, those are representing x values. Over here, those are representing y coefficients, right? So you just look at what are the coefficients here? 1, 1, 1. 1x plus 1y equals 1. And then notice our coefficients here, 1, 1, 1 in the matrix. Okay, so here we have an equation 2x plus 3y equals 6. This becomes 2, 3, 6 in the matrix. And I know, well, my first column, that represents x's. So the 2 must go with my x, so there's the 2x. The 3, well, that's in my y column, so that's 3y. And the answer here in the end is a 6, so it's 6, so 2x plus 3y equals 6. So you pick this up quick. You can go back and forth pretty quickly between a matrix and an equation, right, that you're looking at. So x plus y equals 1 becomes over here 1, 1, 1. 2x plus 3y equals 6 becomes 2, 3, 6. So you can start with the system and convert it to the matrix, or you can take this matrix and convert it back to the system of equations. You generally will do both. But usually when you're converting back to the system of equations, it's probably, hopefully, in its solved form. So you're just converting back to the solution. You're not really converting back to a bunch of work. But it depends on what you're doing. Okay. Now this technically is what we call an augmented matrix. And the augmented matrix sometimes has a line right here. Like most books will tell you to put a line there. Like if you look on page 622 of our book, they say, here's how we write the augmented matrix. But so that line right there is really taking the place of the equal signs in our original system of equations. So see how like these equal signs are just signifying that's where the equals go. Many programs do not by default include those. You can usually do something, you can add a parameter so that it'll make an augmented matrix. But usually you're going to know if you're dealing with an augmented matrix by the context of the problem that you're working on. For this class, we're largely going to be dealing exclusively with augmented matrices. Okay, like in my research, I used matrices that were representing graphs. Like the graph is this mathematical structure with vertices and edges, and you can represent it with a matrix. That's what I was usually using matrices for, so it wouldn't have this line in that same place. But a lot of times, even when that line isn't there, it may still be an augmented matrix, but you would know whether you were dealing with a system of equations or a graph theory problem, right? Because you're going to know what you're working on. So while the book will talk to you about putting this line here as an augmented matrix, when you first use Maple or MATLAB, the default is not to make it an augmented matrix, but everything still works fine. So you just kind of want to know if that line is there or not. Like just realize sometimes the line doesn't get written in there, but the math all still works the same. It's really just to sort of help you remember, oh yeah, those are equal signs essentially right there, but they don't really change the problem. So let's say we wanted to write the system of equations that is represented by this matrix. So, you know, especially if you're new, you kind of go, oh yeah, isn't there like a pretend line right here where the equal signs go? And each, sorry, my throat is so bad today with the allergies. You go, okay, well if each row is an equation and each column is a variable and then a constant, so that must mean in this case, look, we have 3 variables and then our answer. So in this case, we would probably call this negative x minus y plus 0z equals 1. Now, of course, for 0z, you don't usually write in plus 0z. That term would just vanish and go away. So you probably wouldn't write it. Our second equation here would be x plus 2y minus z equals 3. Right, we're just converting right back. This would be, the third one would be x plus 3y plus 3z equals 7. So you can easily recover your equations from the matrix that you're dealing with. So turning a system of equations into a matrix, easy to do. Turning it back from a matrix to a system of equations, easy to do. You just sort of, you can literally go through and label it like I did up here if you need help the first couple times. You'll pick it up quickly, but the first couple times if you want, put an x up here where the cursor is, put a y up here where the cursor is, put a z up here where the cursor is, and then each one of these is an equation, and you just rewrite it out in your equation form. Okay, if anyone's not clear with what I just covered, feel free to ask a question there in the chat, okay? And I can go over that. Okay, and then down here, write the matrix that represents the system of equations here. So in this case, it would be 3, 5, 7 would be the first row. 1, 2, 3 would be the second row, is what that would look like, okay? Right here, write the system of equations that is represented by this matrix. Now here's where, so let's take a look at this. In fact, I keep showing you this thing, but I actually wanted to show you, where is it? Here. I'm going to show you on here so I can type it a little bit. Let's make this bigger. Actually, how do I want to size this? We'll make do with that. Okay, so we've got this system down here. Write the system of equations that is represented by this matrix. 1, 0, 2, 0, 1, 3. So remember, the first column's an x, the next column's a y. These are the solutions to our equations. And then each row represents an equation. So if I go here, let me find where's the code for that. Okay. So doing that, this would become 1x plus 0y equals 2. And 0x plus 1y equals 3. Now this is not how we would normally write it. I'm just, excuse me, I'm just making a direct link between just one step between the matrix and the solutions that it represents. So see how the coefficients are preserved? 1, 0, 2, 1, 0, 2, 0, 1, 3, 0, 1, 3. But of course, we don't usually write equations that way. If I have 1x plus 0y equals 2, I'm probably just going to write that as x equals 2. And the second equation, 0x plus 1y equals 3, we don't write that way. We would write this as y equals 3. Which effectively means we have our solution, right? Well, x is equal to 2 and y is equal to 3. We're done. You just solved that system of equations. So what you want to recognize is this pattern right here where we have a bunch of 1s and 0s in this special pattern. You'll get into more complicated structures that have that pattern of 1s and 0s in this way. But when you see this pattern where you have a 1 and then it's 0s after that and then a 0 and then a 1, really you just get to the point where you can just read this directly and go, oh, well that means x equals 2 and that means y equals 3. Okay. For instance, if we were to look at this one, we would have a diagonal of, it would look like this, where we have a diagonal of 1s, and then 0s above and below it, and then the answers over here. So it would be like 1, 2, and 3. So let me show you, let me steal this. And we'll put it right here. Except instead of A, B, C, it's going to be 1, 2, 3. So if you're unsure, practice going back and forth between these two. This would be 1x plus 0y plus 0z equals 1. In other words, x equals 1. 0x plus 1y plus 0z equals 2 is just y equals 2. If you have a coefficient of 0, that whole variable just vanishes from that problem. So whenever you see a diagonal of 1s and then zeros around it, you know that this thing on the right, those are your actual solutions, right? In other words, this is where we're usually going to be trying to get our matrices, is to a point where they have 0 or 1s down what we call the diagonal. The diagonal would be first row, first position. We have a 1 here. Second row, second position. So second row, second column. We have a 1 there. Third row, third column. We have a 1 there. And then it's zeros above and below those 1s. That's our goal. That's our target. You're trying to get your matrix to that point, or as close as you can get it, depending on the type of solution that you're going to end up with. So this is a pattern you want to be able to recognize, because at some point you'll just start to go, oh, here's my solutions. I know what my solutions are. So here, when I say, well, what can we say about a matrix of this form? What we can say is that that system of equations has been fully solved, right? Now you have to interpret the answer and figure out what the answer is, but the answer has been arrived at. You just have to get to the point where you can sort of recognize what that answer is from the matrix, okay? So let's go ahead here. So how do we do that? How do we get from a matrix which is unsolved, right, which has lots of coefficients to it, to the point where it looks like this, where it's got the 1s on the diagonal, the zeros, and then our solutions? How do we get from the beginning to the end, right? So there's good news here. One is we're going to teach you these row operations, so because you have to understand how row operations work in order to do anything with matrices. But the good news is down the road, once you have a handle on this and you're using this in your upper division work, the whole procedure is going to be algorithmicized. It's going to be, it's been turned into an algorithm. In fact, they talk about it in the book on page, well, they talk a little bit on 626. They do kind of like a lazy version of it. And then they talk about it more in depth on page 631 with, it's called Gauss-Jordan Elimination. And Gauss-Jordan Elimination is basically a way to go through and use these row operations continuously until your matrix ends up in that solved form. Now, doing them by hand is not great, right? I remember taking linear algebra, and it's like you're doing, 12 or 15 row operations, and you make one little mistake in your matrix, and then you got to redo all this work. It's a huge pain, I know, which is why we make you do enough of them so that you understand what's going on with the matrices. But then in real life, once you get that, you go, no, I understand how matrices work, then we just have a computer do them for us, because honestly, it's hard to do without making a mistake. The computer's probably not going to make a mistake when it does it. Okay, but in the meantime, we need to know how those row operations work. Otherwise, you just won't have any understanding of linear algebra. Okay, so we have the following row operations available to us. And we say row operations, that means we're dealing with rows. Column operations are a whole different ball game, so don't worry about those for now. Okay, so the following row operations produce matrices that represent systems with the same solution set. So remember, that's what we would do when we were solving equations, like in beginning algebra. You would do an algebra step and it would change your equation, the way your equation looked, but it would still have the same solution. So that was our whole goal. Simplify the equation down till it just said like x equals 2. Well, that's what we're doing here, is we're trying to simplify that. We want the matrix to represent the same solutions, but we want it to get simpler and simpler so that we can just read the solution right off the problem. So step 1 says 2 rows of a matrix may be interchanged. So we can just take 2 rows and flip them. So see how this top row 1, 2, 3 became the bottom row 1, 2, 3, and this bottom row 4, 5, 6 became the top row 4, 5, 6. That is a perfectly allowable move to do in matrix manipulation. We can just flip the rows with each other. Now, why is that allowed? Well, if you go back, because it's important to understand why you can do these things. If not, again, you don't really understand what you're doing. Well, what did we say up here with our matrices? We said that each row represents an equation, right? So that means that in the matrix, if I flip two rows with each other, that's just the same as going back to my original equation and just flipping the two equations. Well, if I wrote this system as x plus y equals 1 over 2x plus 3y equals 6, or I flipped those and made it 2x plus 3y equals 6, and then the second equation was x plus y equals 1, we could probably all agree, like, yeah, we expect to get the same solutions either way. If you just swap your two equations with each other, you don't expect it to change the solutions, right? So that's all that's really happening with row operation 1. You're switching two rows, which is the same as just writing two equations in a different order. It's not going to change it. So that's why that's an allowable move, right? And it doesn't seem like that big a deal, but it's very, very helpful sometimes. When you're doing these row operations, there's different ways to go through there. One person will see like 2 moves they can make and it like fixes everything. Other people will end up making 12 along the way. That's why we have Gauss-Jordan elimination, is because it simplifies the steps so that you're just always sort of following what ends up being a relatively straightforward move. Okay, row operation number 2. The elements in a row may be multiplied by a non-zero number. So don't multiply by 0. That's the same as just erasing your equation and we lose all that information, right? But we can multiply an entire row by a non-zero number. So look here, we started off with 1, 2, 3 over 4, 5, 6. And now it's become 2, 4, 6 over 4, 5, 6. So what happened? I took row 1 and I multiplied it by 2. So 1, 2, 3 became 2, 4, 6. And it's reasonable to go, okay, now that's got to change things, right? You just changed all the coefficients to something different. No, it's the same matrix. It's going to have the same solutions. Why is that? Well, if row 1 represents an equation, then what happens when we multiply the entire row by 2? Well, that's like taking the original equation and multiplying the whole equation by 2. And you've done that a million times, right? When you were solving different problems, say you can multiply the whole equation by the same thing and you just do it. Well, that's all we're really doing here. When we multiply a row by a non-zero value, that's the same as multiplying the equation by a non-zero value. And you're allowed to do that as long as you multiply everything, right? So that's why C is a legitimate move, because it doesn't change the solutions because you're just multiplying an equation by a non-zero number. Okay. Right, so that's row operation number 2. Row operation number 3, now this one gets a little bit more complicated, and this one's a little harder to justify. You'll actually, when you get to linear algebra, your professor will probably show you, or your book will show you why this is a legitimate move, but it's a little harder to explain why this is allowable as when we're just learning matrices, right? It takes a little bit longer. But row operation 3 says the elements in any row may be multiplied by a non-zero number, and these values may be added to the corresponding elements in any other row. So that, it sounds like 2 operations, but it's a combination of the second row operation and a new one. And sometimes people get confused then because they start going, oh, well, does that mean I can just add the same value to an entire row? No, you can't do that. You can't take an equation and just add 4 to each term. That's not allowable. But what you can do is take a multiple of that row and add it to an existing row is basically what we're doing here. So, oh right, I don't even have that one written out because it gets a little harder to justify. So, for instance, I could take 2 times the top row and add it to the bottom row. That's allowable. Right? And you might go, oh yeah, well, what is the justification for why we can do that? And like I say, you got to wait till linear algebra. But the truth is, you've already been doing this. This is what you do when you do the elimination method. You multiply your equation by something, and then you add it to another equation, right? That's exactly what row operation 3 says. Except here we're doing it with rows. I'm taking a multiple of one row and adding it to another row. That's elimination, where you take a multiple of one equation and add it to another equation. So you kind of already believe that this is allowable, and it is, but it's it's beyond the scope of this class to really explain like how. Okay, so what do you do, right? So here we have a system where I started off with 2x plus 3y equals 5, negative x plus y equals 5. And we want to solve this system of equations. Well, what I have down here is a series of steps, and if we were in class, I'd kind of have you play with a little bit, but we don't have enough time. See how we start off with the matrix that represents this system here? Like it's exactly this. 2, 3, 5 is our first row. Negative 1, 1, 5, that's our second row. Okay. Our goal is to get it, remember this is our target where we have these ones. So the first row, first column is a 1, second row, second column is a 1, and then we have zeros above and below that. That's the pattern we're trying to get to. So your whole goal is to get from this sort of chaotic mess over to this organized mess over here. Okay. Well, how did we do that? Well, you just want to work through your rows, basically. What you generally want to do is get the first one in the right position and then get zeros above and below it. Then go to the next row, get your 1 in the right position, get zeros above and below it, and you just work through it. If you do them out of order, sometimes people go, oh, I see a shortcut, I'm just going to do this step really quick. If you don't do them in the right order, you're going to end up undoing your previous work, and then it's a bummer when you've done like 4 or 5 steps, and then you're like, wait, I already fixed these spots, but now they're the wrong values again. That's because you have to do them in the right order. Otherwise, your work doesn't stay put. It gets messy again. So step 1 is generally to get a 1 up in this upper left column. So what I did was I first said, okay, well, if I want to get a 1 up here, and this is where there's different choices about how to do it. Okay, but I'm just showing you one way. Well, what if I swap the 2 rows? So step C is a row swap where I flip those 2 rows. Why did I do that? Well, it put a negative 1 up here, and I can turn a negative 1 into a positive 1 using row operation 2, which is to multiply, I'll just multiply that whole row by negative 1. So we had one step that flipped our rows, swapped our rows, and the next step multiplied the top row by negative 1. Now look, we have a 1 where we want it. We have a 1 in the first row, first column position. That's what we want. And then immediately we want to get zeros in the rest of that column. So how do you do that? Like, what is this E move? How do I go from here to here? Well, what I did was, I forget, what did I do? Looks like multiplied everything by 3. Wait, what did I do? Oh, yeah, right. Well, actually this step is C0, 5. Must be a linear combination, so I must have taken negative 2 times the first row. Oh, yeah, okay. I think that's what it is. I took negative 2 times the first row here and added it to this one. All right, sorry, I just lost track for a second. So basically what you want to do is you ask yourself, how do I get a 0 here for the 2? And usually that's row operation 3, because you're going to take a multiple of this row that has a 1 in it, and you're going to add it to down here to get that 2 to become a 0. So if I take negative 2 times this top row and add it down here, and add it to this, yeah, negative 2 times this, and add it to this down here, that's row operation 3. Negative 2 times row 1 plus row 2 gives me this. So see how my 2 became a 0? That means now, unless I do something really weird, this first column is locked in place. That 1 and 0 aren't going to change. So that's why when you get the 1, you get the zeros in place to lock that column. Otherwise, it's going to stray again and become a mess. Then your goal is to move to the second column and figure out, well, now I need to get a 1 here where the 5 is. I need that to be a 1 because I need it in the second row, second position. So what I did here, I just multiplied row 2 by 1/5, and it gave me 0, 1, 3. So that's row operation 2. when we say we can multiply by something, you also can think of that as dividing, because multiplying by 1/2 is the same as dividing by 2, right? So, okay, great. I've got 1's in the right position. I've got a 0 here. Now I just need a 0 up here. Well, all we have to do is add, so row operation 3 again, we're going to add 1 times row 2, which is just row 2, plus row 1, and we get this. So we get to our desired value, that target value for our matrix. And now I can just read it. Oh, this means that 1x plus 0y equals -2. And 0x plus 1y equals 3. In other words, x equals -2, y equals 3. That's our solution. And we could even go back up and check it. Let's see. If I put in -2 plus 3, that's going to be -4 plus 9. Yeah, that's 5. And it works in the other one too. So that's how you use those steps to solve your system of equations. Okay? And I have this problem at the end. Usually just so students can get practice, like going through those matrix row operations to try to get it taken care of. You're free to practice that. You're also going to do some on the homework, so you'll get a chance to mess with that anyways. So let me just see real quick if there's anything else I want to say. Got our matrix row operations. The matrix row operations I showed you are on page 624 in the book. So I'd encourage you to keep those up, to look those up. They also have a nice handy notation they use, which can be helpful to know. It's just easy to keep track, because once you have a bunch of matrices written there, like I know there's a tendency to I'm just going to write them down, I'll remember. And then you go to the bathroom or you go have dinner and you come back and you're like, oh, how did I get all these matrices? Where do they come from? And then you got to work your way through how you got each one. Is kind of a pain. So if you make a little note to yourself, like, oh, I took -2 times row 1 and I added it to row 2. That can be really helpful when you're going back and trying to find a mistake or figure out what you did or pick up a problem you've already been working on. That notation's really handy. They talk about Gaussian elimination using back substitution. That's just a way of kind of stopping halfway through. So halfway through your matrix being solved, you can stop, and using back substitution, it's like what we do with the system of equations, where you've got like an x, y, and z, and you get z, then you go back and use that to solve for y, then you go back and use that to solve for x. That's called back substitution. But if you solve the matrix completely, you don't have to do that. And especially since you're usually going to have a computer doing it for you, usually you're not going to stop halfway through. You're just going to say, finish solving it for me, and then you're going to do it that way. So they talk about the back substitution, but then they give you the full Gauss-Jordan elimination on page 631, and just kind of they have you work through it. So this is really nice because, like, when it comes to systems of equations that are 2 equations and 2 variables, it probably takes you about as long to solve it by hand as it does to put it in a computer and have the computer solve it for you. It's like you're not saving much time. But by the time you get to even 3 equations and 3 variables, it's going to be quicker to put it in a computer. And certainly by the time you get, say, 5 equations and 5 variables. And because of the vast amounts of data and computing power we have, most systems of equations in the modern world are large. They're not ones that you would want to solve by hand, right? So it makes sense. Throw them in a computer, have the computer do it for you. As long as you understand what's happening, that's perfectly legitimate. Okay, so that's the discussion on, yep, looks like I got everything for 6.1. So next time we'll pick up with 6.2. I like I say, if I probably will have to, but worst case scenario, I'll go get the tests physically in my hand on Monday, and I'll have those tests for you posted on Monday so that you can figure out what you want to do about the retake. Otherwise, I will see you later. Anyone who wants to talk to me in Zoom, please feel free to do so. Otherwise, I'm going to shut down the stream, and have a good weekend, and keep working hard. You're almost there. A couple more weeks. You almost got it taken care of. Okay, thanks everybody. We'll see you later.